Topic 3.3 Standard Test Methods and Interpretation. And for this topic, we move on to hardness test, and it's also known as indentation hardness test. When you look at this picture showing the impression on the metal surface, and here is the concept of hardness test is to measure hardness by introducing indentation onto the metal surface. And so the deeper or the wider the indentation, the softer the metal is. And since we have a wide range of metallic materials, therefore for the test, we use different types of indenters and different levels of load, depending on the test standards and materials or components to be tested. Over here, I introduced you 4 types of hardness tests that are normally applied for metallic materials. The first one is the Brinell hardness, following the ASTM E10, and the second one is the Rockwell hardness, following the ASTM E18, and the third one, Vickers hardness, that can be either in the micro or the macro scale, following ASTM E384 and E92 respectively. And the last one is for the noob hardness test that is normally used to measure the hardness in restricted areas. And you can find all the test standards online, and all the updated versions are also available. So when we look at these 3 samples of different metallic parts, first one is the nitride steel gear. The second one is the aluminum casting, and the third one is brass fittings. So by the end of this topic, you'll be able to choose what type of hardness test that is suitable for each metallic part. So now let's start on the first standard hardness test, the Brinell hardness indentation, following the ASTM E10. Over here, you can see the example of Brinell hardness testing machine. We have the specimen set up over here and the display for user-friendly. And if I enlarge the specimen set up over here, you can see that over here is the steel ball as an indenter having the diameter of 10 mm. And once we apply the force ranging from 500, 1000 to 3000 kg force onto the metal surface sitting here on the stage. So we can have the Brinell impression like a crater on the metal surface. To measure the impression, I would like you to have a look at the cross-section over here. There is the steel ball indenter having the diameter of capital D, and once we're making the impression on the metal surface, we now have the impression of the diameter small d. So on applying the load for a standard time of about 30 seconds, we then measure the diameters of the indentation at right angles, as you can see from over here. The impression have 2 diameters normal to each other, which are D1 and D2. The average of these 2 readings will give the measurement of Brinell hardness number. So after averaging the 2 readings of D1 and D2, we have the Brinell hardness number in the unit of BHN or HB, that is expressed as the load divided by surface area of the indentation. And normally we can read out from the hardness chart. This slide shows you the example of 3 materials, which are aluminum, brass, and the last one, iron and steel. These 3 materials having different levels of hardness, therefore we have to apply different load scales. For aluminum, we have to apply 500 kg force, and for brass, we have to apply 1000 kg force, and for iron and steel, we apply 3000 kg force. And so, if I give you 3 examples of this, can you select a proper level of load that apply onto the metal surface while we're doing Brinell hardness test? This part is cast from aluminum, and therefore we have to select 500 kg force when we do the testing. In the middle, there are brass fittings, so the suitable load scale is 1000 kg force, and the last one is the turbocharger made from cast iron, and therefore 3000 kg force is the most suitable load level. Here I would like to summarize the advantages and limitations when we use Brinell hardness indentation. So first, let's have a look on its advantages. the indentation large so that it can average out local heterogeneities of the microstructure. It means that we can sampling the test data over a large area. Second, different loads are used to cover a wide range of hardness of commercial metals, ranging from the softer materials like aluminum up to iron and steel, which is much harder than aluminum. And third, less influenced by surface scratches and roughness than other hardness tests, quite relatively larger indentator of the steel ball having 10 mm diameter, and therefore the test results is less sensitive to surface scratches. Before we doing the test, we have to cut the metal piece and grind on the surface to make it flat and also smoother the surface. And by using Grinnell hardness test, we can prepare the metal surface just on grinding. It's not necessary to go for polishing step, and this will save a lot of time for us to prepare the sample. Let's hear some limitations. Since the indenter is large, it's not suitable for small specimens or where we have to do the test at critically stressed parts because it may not be feasible where the indentation can cause the failure. And second, because we have to take 2 readings of the diameters on the impression. Therefore, it is possible that there could be human errors by measuring the diameters. So these are advantages and limitations. If you have to measure the hardness for big metal components, so you'll be able to choose Grinnell hardness indentation. And the next one is Rockwell hardness indentation. This type of hardness test is well recognized in metal forming operation plants because it is quick and excludes the human errors by reading the parameters on impressions. This type of hardness test following the ASTM E18. Over here, you see the Rockwell hardness testing machine with the specimen set up down here and the display. There are 2 types of indenter. The first one is the steel ball having 1/16 inches diameter, and the second one is the diamond cone, and we call it the Brill indenter, having the included angle of 120 degrees. When we apply the force rating from 60 to 150 kg force, depend on the scale of the hardness, we then have the impressions on the metal surface. The first one on your left-hand side is the indentation obtained from a bowl-type indenter, and one on your right-hand side is the Brill impression. For Rockwell hardness test, there are a range of scales, but for now, I will introduce you just 3 scales: HRA, HRB, and HRC. For each scale, we have to select proper indenter and the major load so that we can get the standard test result. For example, on scale A, we have to use the diamond or the Brill indenter and also apply the major load of 60 kg force. And for scale B, we now change into a steel ball indenter while we increasing the major load up to 100 kg force. For scale C, which is suitable for surface hardened steels, we use the diamond or the Brill indenter with the major load of 150 kg force. And for the instruction of the test, we first have to position the surface area to be measured close to the indenter. Over here, you can see the indenter attached onto the indenter holder. Specimen to be measured placed over here on the stage. And if I enlarge the view over here, you can see that on top of it is the indenter, and down here is the sample surface. To do the test, we have to first apply the minor load, as you can see from a position here. And this is to locate the location that we would like to do the test by applying very small level of load over here. There's very small indentation taking place over here. After that, we set this level as a 0 reference to position at A. And then the major load is applied for a specified time period or the dwell time. Then we arrived at B, which is the penetration depth by applying the major load. And after that, the major load is released having the minor apply load at C. And you can see that from B on red line to C on green line is the elastic recovery released by the metal surface that had been deformed at the first place. So the actual penetration height can be measured from A to C, as the values of Rockwell hardness is measured by the depth penetration, as you can see from this picture. Over here on the top of the metal surface is the brow indenter, and by applying the major load of 60 kg force onto the metal surface, down here along the depth of metal surface, there are 100 divisions, and each division equals 0.002 millimeter. So remember, the deeper the penetration depth, the softer the material is. So for example, if the penetration depth equals 30 divisions, and therefore the Rockwell hardness test will give the value of 100 division minus 30 divisions, which is 70 HR. And to make it more easier for you, you can apply these two expressions for brow and bow indenture. For the brow indenture, the Rockwell hardness can be obtained by having 100 minus h over 0.002 millimeter, where h is the depth of the indentation. And for the bow indenter, we can calculate the Rockwell hardness as 130 minus h over 0.002 millimeter. And so let's have a look onto this slide showing examples of materials that can be tested by using Rockwell hardness indentation for different scales. The first example is the tungsten carbide. The second is copper. The last example is the hardened steel. And you can see that the hardness scale that's most suitable for tungsten carbide is HRA, while brass and aluminum can be tested by using HRB scale. And for the metallic materials like hardened steel, it's most suitable to use HRC hardness scale. And then I would like to summarize the advantages and limitations of Rockwell hardness test. First, on the advantages, as I said before, this type of indentation test is the most widely used in the US and generally accepted around the world due to, first, its speed, and second, freedom from personal error, because the machine will show the values without us reading the indentation parameters. And third, because of the wide range of scale that can be applied. So it has the ability to distinguish small hardness difference between different materials. And lastly, the size of the indenter is not big, so it's good for many sizes of metal to be measured. And now let's see some limitations. And because we use different scales to suit different materials, so we have to remember what kind of lugs and indenter to be used in particular metal, so care must be taken to account for during the test, or you will come up with the wrong data for interpretation. The third technique is the vigorous hardness indentation, and here I introduce the example of vigorous hardness testing machine. Here again the specimen setting, and we can apply the load instruction over here. And out there is the microscope that we can locate the specimen surface and to measure the diagonals from the indentations. As I said before, the vigorous hardness can be either in the micro scale or the macro scale. The micro scales following ASTM E384 using the applied load ranging from 10 gram force to 1 kilogram force. And for the macro vigorous hardness, we apply the load ranging from 1 kilogram to 100 kilogram force. And for the indenture itself, we apply the diamond pyramid, as you can see from the picture over here, having the included angle of 136 degrees. And since the indenture has a square base, once we apply the load onto the metal surface, now we can have the impression looking like this. So in this case, we have to measure two diagonals at right angles, which are D1 and D2. Over here, the example of vigorous impression on the metal surface, that you can see the perfect square indentation required for accurate measurement of the vigorous hardness result. To measure the diagonals, we normally look through the microscope and use the software to operate, giving two readings of D1 and D2. To do the test, we first apply the load for a standard time on the flat and polished surface. This is very important because hardness is very sensitive to scratches. You can't measure the metal surface by using vigorous hardness indentation without polishing the metal surface. So it takes time to prepare the set, and therefore it's not normally used for those who's involved in the metal operations. But this type of test is normally used for research and those who are involved in advanced materials. And once we apply the load on, we have to measure the diagonals of the indentation at right angle using an optical measurement system as shown on this picture. After averaging the two readings of diagonal 1 and 2, we now arrived at the vigorous hardness number with the unit of VHN, and it is defined as the load divided by the surface area of the indentation. And you can see that Brinell and vigorous hardness roughly defined by the load divided by area, and they are different from Rockwell hardness, which the test data is recognized by measuring the depth of the indentation. Over here, I would like to emphasize a bit about how to obtain the perfect indentation required for accurate data by using vigorous hardness indentation test. We have to select proper load level for different types of materials to be tested. And if we don't choose the correct load level, we may come up with the pin cushion or the barrel indentation that will give you some errors on the reading. First, on the pin cushions, over here, if you recognize that we have to measure two diagonals, and if we have the pin cushion, we now get the overestimated diagonal length, and that means the hardness result will be softer than it should be. And this will observe in the anneal metals that we have to be careful about. On your right here, if the indenter has the barreled shape like this, crossing here are the diagonals that we have to measure. And you can see that the diagonal lengths are underestimated. And this means you will get the hardness values that is higher than it should be. And this result may be observed in the cold worked metals that you have to be careful about. So what we need is to obtain the perfect indentation with a square base like this to give the accurate result. These are the examples of the materials that can be tested using vigorous hardness indentation. Over here is the 316 stainless steel, as you may recognize as the military knife used in Switzerland. This gives the hardness scale of 140 HV, and the number here showing the load scale that we apply onto the sample. And on the right here is the carbon steel, and that will give you the vigorous hardness number of 55 to 120 depending on the grade of the carbon steel. I would like to summarize the advantages and limitations for vigorous hardness indentation. First on its advantages, it can be used to test on a variety of materials ranging from metals, ceramics, composite, and almost any types of materials. Second, it is widely accepted for research work due to continuous scale of hardness for a given load. And third, we can employ vigorous hardness indentation tests to very thin materials like foils or surface of a part or even small parts with small areas. We can also measure the microstructures of individual phase or the depth of the case hardening that are possible by using micro vigorous hardness tests that I will show you later. Even though there are quite a range of advantages, here are some limitations. First, it's not widely used for routine check of the industrial work due to a slower process and requires careful surface preparation. Remember, we have polished the surface, not just grinding. And it is possible for human errors by measuring the diagonals. And it is important to have the operators that have been trained properly. And another type of vigorous hardness test, as I said before, we can apply small level of load to obtain micro hardness indentation. And for this type, we can either use the vigorous diamond pyramid indenter or the nude diamond pyramid indenter. As you can see that diamond pyramid comes with the square base, but the nude we have the reduced dimension along here, so it's appropriate to measure the case hardening of the metal surface. So we have to select either the vigorous or the nude indenter. And for the force, it can be ranging from 5 to 1000 gram force following ASTM E384. And with this small indenter size, we can determine hardness over a very small areas. For example, on individual constituent phases that requires hardness testing machine in the micro or sub-micro scales. So I'm giving you the example here. You might not see this picture before. It is the microstructure of the cast iron showing different phases when we look under the optical microscope. Giving you a little bit more details on here. The phase that is looking spherical here is the graphite. Surrounding it is the ferrite, which is softer than the matrix lying over here. And you can see the laminar structure of the pearlite. Delineated along the arrow here is the carbide, which is the hardest phase. And once we apply the vigorous indentation onto individual phases, you can see that first we have very small indentation here because we have done the test onto the hardest phase. Here comes we have very small diagonals from the square base here. And the next one, we apply the indentation on the pearlite phase, which is softer than the first one, which is the carbide. Now the indentation becomes bigger with longer diagonals on the square base here. And the third example, we apply the indentation on the softest phase, which is the ferrite. And this is the softest among the three phases. So we can see that vigorous hardness indentation test can tell you the different hardness data on different phases in the microstructure, and therefore is useful for research and development. Another example here on your right hand side is the indentation of the new indenter applied onto alumina of 99.5%. Normally, new indentation is applied for thin surfaces. And finally, I would like to summarize all the indentation hardness tests over here, ranging from the type of the test, the indenters utilized, and what happened when we apply the indenter on the metal surface, and also on the top view. When we obtain the load, we can calculate the hardness number according to the formula provided the column on your right hand side. Firstly, on the Brinell, we use the steel ball diameter of 10 mm, or we can also use the tungsten carbide ball as well. That will produce the indentation diameters of small d, as you can see from the top view here. The load measured can be used to obtain the BHN value by putting on this equation to give the Brinell hardness number. And for vigorous hardness test, we apply the diamond pyramid with the square base of 136 included angle to produce the indentation on the metal surface of the square base here like this. By measuring two diagonals normal to each other, we can now calculate the VHN or vigorous hardness number by putting the load measure and average value of diagonals over here to give the vigorous hardness number. And for the new micro hardness, we apply the diamond pyramid with a narrow dimension over here onto the metal surface by using a small level of load. And to calculate the new hardness number, we put in the load and the L dimension here to give the new hardness number. The first three will give the hardness number based on load divided by the area. And for the Rockwell hardness test, it is different by measuring the depth of the indentation. But actually there are a range of scales. The first group showing the scales that apply the diamond cone indenter, which are HRA, HRC, and HRD, by applying different levels of load of 60 kg force, 150, and 100 to give different Rockwell hardness scale. And next, we use the steel ball to give HRB, HRF, and FRG by applying different levels of load, for example. And here are the summaries of the standard test method for hardness test for metallic materials. And I hope that you can choose the appropriate technique and test method for your applications. Although there are other types of hardness tests like superficial hardness test or nano indentation hardness that I do not mention in this course, but I think the hardness test that I have given you would be sufficient for now.